Hello everyone, I'm Jiakun from Zhejiang University. Today, I will talk about the introduction and removal of different types of technical debt. Technical debt is a term to describe a compromised decision that sacrifices the code quality for the time. For example, code smell, code classes, and duplicated code. This figure shows that technical debt is bad. The technical debt can lead to the increasing burden in the future. For example, can have more bugs and more changes. Considering the negative impact of technical debt, previous study investigated the management of technical debt. For example, they characterized the introduction and removal of all technical debt during the development process. They also designed a series of categorization to characterize the technical debt. However, they only focused on certain types of technical debt or all types of technical debt. For example, observing the introduction and the removal of code smell. This is because that technical debt is often not directly visible. Researchers have to perform a thorough analysis of the whole project. None of the previous studies characterized the removal of different types of technical debt at the same time. To fill this gap, we use the self-admitted technical debt, that is SATD, as an indicator of technical debt. More specifically, such technical debt is the comment that is intentionally introduced by developers to alert the improper of the solution and is acknowledged by developer. For example, in TensorFlow, a comment saying that identify why this infrequently causes timeouts shows that the corresponding code is problematic and needs further investigation. To find the common patterns on how developers remove different types of technical debt, we use the introduction and removal of SATD instances in a family of software systems as an example, that is deep learning frameworks. This is because we would like to choose a homogeneous set of projects from the same domain to minimize the domain confounding effect. The field of the development of different deep learning frameworks is the same, that is, offering high-level programming interfaces to deep learning applications by implementing a range of the same tasks, that is, core building blocks for designing, training, and validating deep learning neural networks. Moreover, deep learning frameworks are the most important software systems today due to the wide use of deep learning applications in health, cars, and some life-impacting software. Therefore, the effective and efficient maintainability of deep learning framework is important. However, the deep learning framework related techniques are still rapidly advancing with some cutting-edge technologies. Developers have to implement this novel technique in time to win the fierce market competition. This could increase the risk of technical debt at the same time. In our paper, we include 7 deep learning frameworks. We extract the comments in all of the file history, identify technical debt using an NLP-based tool. Then, we manually classify technical debt into different categories. Such categories are the same as previous studies, that is, design debt, documentation debt, defect debt, requirement debt, test debt, algorithm debt, and compatibility debt. With this data, we answer the following question. The first question is, which types of technical debt are previously introduced along the development process? This can reflect which kind of suboptimal trade-offs are made by developers during the development process. We find that design debt is the most common, followed by the requirement debt and algorithm debt. Documentation debt is the least common, followed by the test debt. Then we answer which types of technical debt are removed the most. We first characterize the distribution of different types of technical debt among the removed technical debt instances. This can reflect the allocation of developers' efforts in the resolution of technical debt. Then we characterize the proportion of the removed SATD instances among introduced SATD instances for different types of technical debt. This can reflect which types of technical debt are removed the most to finish the development task and to ensure the code quality. We find that requirement debt is removed the most, followed by the design debt. Documentation debt is removed the least, followed by the test debt. Then we answer which types of technical debt are removed the fastest. The survival time of the technical debt can illustrate the priority of different types of technical debt when developers resolve them. We depict the survival function of different types of technical debt in different projects. We find that design debt is removed the fastest, followed by the defect debt. Compatibility debt is removed the slowest, followed by the test debt and the documentation debt. Finally, we answer who removes different types of technical debt. It is expected that the technical debt is self-removed, that is, removed by the developers who introduced it. As a result, documentation debt and defect debt is the least self-removed. Test debt, design debt, and requirement debt are the most self-removed. Compatibility debt and documentation debt are the most removed by the developers with more activities in the project. We plot the evolution of the frequencies of different types of technical debt along the development process. We would like to use Keros as an example. At the beginning of the development of Keros, requirement debt is the most common. Developers are confronted with the fast iteration of the project and they record the unimplemented task. After that, the number of design debt increases along the development process and become the most common design debt, technical debt. Many SATD instances are written down to express their dissatisfaction with the design of the code. Meanwhile, the number of algorithm debt instances increases and becomes the second most common technical debt. It shows developers concentrate on the algorithm, and currently, compatibility debt increases step by step and becomes one of the most common debt now. This is because that Keros does not handle low-level operations that are tensor products. This leads to that Keros enjoy the convenience provided by the backend project at the cost of maintenance of the dependencies. Based on our findings, we provide implications for practitioners, project managers, and researchers. For example, we suggest the project managers should take the evolution of the frequencies of SATD into consideration when managing their projects. They should find a balance between the quality of the project and the proposal of new requirements. In summary, in this paper, we characterize the introduction and removal of different types of technical debt. To do so, we use the SATD as an indicator of technical debt. We use a homogeneous set of projects from the same domain to minimize the domain confounding effect. We use an NLP-based tool to identify SATD comments and manually classify the SATD comments into different categories. And we finally depict the evolution of frequencies of different types of technical debt along the development process.
Okay. So I think we are live now. Welcome to the question and answer session. I am Mika, and this is Jiakun to answer the questions. Okay, we have questions from the audience. First from Huang. How do you define design depth versus requirement depth? And are these different types of depth mutually exclusive?
Yes. In fact, I think this question is the same, similar to the next question proposed by David Fussi. I think the design that is related to the design of the code, but the requirement that is related to that the coding task is not complete. So it is the different, but sometimes they are have some overlap. For example, since our SATD is manually labeled, so some of them can be labeled either into the design debt or requirement debt, and this is the most threats in our work. I think this question is similar to the David Fossey, and he says that can you elaborate how you measure requirement debt? Yes, I read the comments in the code, and I found that some of the requirement debt is related to that. He said that this function is not haven't been fully implemented. So that's my answer. Yeah.
Yeah, so it's basically features that are somehow missing. Coming back to the first question, I'm just curious, did you always agree with, according to all the authors, that this is designed this as requirement, or were there sort of borderline cases?
Yeah, in our paper, we have proposed some comments that is the borderline of the design diet and the requirement diet, but I cannot figure out that in the question answer. Please refer to our paper in the threat valid section. Yeah. Yeah.
Okay, so the next, David one. Yeah, so something was missing. So next question from Bo Yang: why only deep learning frameworks, and can the conclusions be generalized to other fields?
Yes. In fact, we only consider the deep learning frameworks because we would like to use a set of the same projects, the project that achieve the same task, so that we can find some common patterns to find the removal and the introduction of different types of technical debt. If we use the projects across different fields, we cannot find the common pattern to remove and introduce the different types of technical debt. As for why we use the deep learning frameworks, it is because that deep learning frameworks is important nowadays, and the technique algorithm related to deep learning frameworks is nowadays still rapidly growing, and the developers have to implement the cutting-edge deep learning algorithms to win the fierce market competition. So we use the deep learning frameworks based on the 2 points. One point is that deep learning frameworks is important and still rapidly growing. This rapid growing can introduce many SATD. And the second is that we would like to use the projects that could achieve the same task. And the question is, can the conclusions be generalized to other fields? I think we would like to propose a framework how to analyze the introduction and removal of the different types of technical debt. The approach to analyze is that you should analyze the same the projects with the same task. Yeah, that's my answer. Yeah.
Okay, we go to the next question from Ham. And he says, in my project's documentation depth is very high, but it is difficult to quantify or describe how serious it is. So how do you quantify or count documentation depth?
Oh, I think this question is far from my research, far from this paper, because I only count the number of documentation depth by counting the number of the documentation, the comments that indicating the documentation depth. So how do I quantify the documentation depth in practice? I would like to ask my workmates if they could correctly understand my code, if they use the documentation I wrote. If they cannot, I think the documentation that would be great. So if in practice, from my personal perspective in coding, so I would like to quantify the documentation data from my workmates. Otherwise, but in this paper, I think I only count the number of the documentation data.
Yeah, I think this is a general pattern in the SATD research, that maybe there should be a sort of new branch where you actually look at the how serious certain depth is, rather than just counting. So that would be an interesting new avenue. Okay, so let's go to the next question from Sridhara Chimala Konda. Are there some definitions and metrics for different kinds of depth? Documentation, design depth, and so on.
Oh yeah. yes, the definition of the different types of technical debt is defined in previous work. So because our we focus on the introduction and removal of different types, and I would like to sell my paper of the introduction, the evolution of the technical debt. So I did not to introduce them in the presentation. In fact, you can find the definitions in our paper. So I would like to give a brief introduction of them, because, for example, the design data is related to the design of the code. The function is okay, but the design, the code implementation is ugly, and the requirement is that the code cannot satisfy the implementation. The fact is the code cannot behave good. Documentation is that the documentation is missing or inadequate. For example, test is the test that is not test use case is test cannot cover all the code, and the competitive test the dependencies is immature algorithm that the performance is like down because of technical debt. So it's a brief introduction. Yeah.
Okay, and the next question from Marion Wiese. She asks, how did you identify documentation depth and the removal of this from the code base? Isn't the most documentation depth not visible in the code?
Yes, I would admit this is true, because the most documentation is recorded outside the code. So in our paper we only concentrate on the documentation that inside the code. Yeah, I would admit this, and I would encourage the future researchers to focus on the documentation that is, for example, the out of the code.
Yeah, so this was more like, missing Java doc comments, all the sort of requirement documents. Okay.
Yes.
Yeah. Okay, so the next question, how have you identified SATD removals? Is the removal based on when SATD comment disappears from the code? Based on the previous study, SATD removal may be accidental. Did you account for this accidental removal in your study? From Fiorella Zambetti.
Oh yes, SATD can be removed by accidental. Yeah, I admit. So yes, we encourage the future developers to do this, because we only take the comments into consideration. Yeah.
Okay, so this is more like a comment from Grace Lewis. This question is also related to previous talk. If requirement depth is defined as missing functionality, is it really technical depth?
In our classification, we would like, yes, I would like to answer yes. If the requirement that is missing functionality because the code isn't fully accomplish the functionality that is required in the documentation or in the requirements, I would like to take it as a requirement. For example, in our comments, I found a lot of the comments that indicating this function is not implemented.